everyone, and welcome to week 4 of our remediation assignments. And this week we are going to be looking at and reviewing some basic concepts of bonding, so the bonding between atoms. And so before we get started, let's look at our mind map this week. And we'll kind of expand this until you can see it because it is kind of small. And a PDF of this will be posted in your modules. So we're going to talk about kind of the bonding between atoms, which can take, part either we have covalent bonding, where the atoms are sharing electrons, or ionic bonding, where you have ions forming and the attraction between ions. And that different type of bond between atoms will lead to substances with different properties as a result. So we'll kind of make those connections today and kind of review some of those. Always look back at your original notes. But before we kind of get started with this, we are going to review a little bit about Lewis dot structures, because we need to remember what Lewis dot structures are all about in order to really understand the bonding between the atoms. And so Lewis dot structures, you might hear them called electron dot structures. Remember, these are models that show how the electrons are being shared or exchanged when bonds are formed. So it is kind of a notation to represent the sharing of or the exchange of electrons between atoms. The Lewis dot notations or Lewis dot structures for ionic compounds and covalent compounds, they do look different because they are modeling different types of bonding. And so let me fix this slide here because we need brackets. And so as we look at these different types of Lewis dot structures, for ionic bonding, we are modeling the transfer of electrons, so how the metals lose electrons, the nonmetals fill up their octets, and then you form ions. And so the Lewis dot structures demonstrate the ions that are formed, the number of ions that need to form for the charges to balance. And they show the full octet around the nonmetal, and they show how the metal has lost its valence electrons. So remember, when you see like the lithium ion, the fact that there's no dots here doesn't mean there's no electrons. It just means it's lost its valence electron. For covalent bonds, those Lewis dot structures are showing how electrons are shared between atoms to fill up those octets. And so one pair of electrons shared between two atoms is a single covalent bond. And remember, atoms can share multiple pairs of electrons if they need to get a complete octet. So they can make double bonds and triple bonds and share 4 electrons or 6 electrons if they need to. In this case, water can fill up the octet of the oxygen just by sharing and making a single covalent bond between the hydrogen. And remember, there are elements that are exceptions to the octet rule that don't require that octet, and hydrogen is one of them. Its happy number is 2. And so it has its one valence electron, but it won't never make more than a single bond between it itself and another atom. Okay. And remember, there are exceptions that also have substances that can have more than an octet, and they can have those expanded octets. So we talked about sulfur and phosphorus. Right? So remember those kind of as we talk about things. So as we talk about bonding, the one thing that kind of determines the type of bond that's going to happen and whether or not you're going to get an ionic bond or a covalent bond is the electronegativity difference. And so let me kind of make this bigger. And so that bond type is formed by looking at the difference in electronegativity. And remember, the electronegativity is it's a property that and it's one of the periodic trends that we looked at, and it's unique because it only is used or determined from atoms in a bond. So remember, electronegativity is the ability of an atom to attract electrons in a chemical bond. So it was the only one of those trends that dealt with chemical, behavior in a chemical bond. There's two ways of looking at this. You can do the straight electronegativity difference, and your teacher may have said the cutoff for the difference between the atoms is like 1.8, and above 1.8 or 1.5 or 1.8, you have covalent bonds, and below, and I'm sorry, um, when the difference is below 1.8, you have covalent bonds, and when the difference is above 1.8, you have ionic bonds. You can also take that difference and make it into a percent, and you get percent ionic character. And so this graph is really looking at the different, the relationship between, percent ionic character and electronegativity difference. And so what you see here is that, for substances where the percent ionic character, and these would be elements that have a very large difference in electronegativities, you tend to get ionic bonds. And when the difference in electronegativities is smaller, that's when you get covalent bonds. 50% is really an arbitrary cutoff. It's the idea that majority rules. So if something is more than 50% ionic, it's considered an ionic bond. And the difference that your teacher used of like 1.5 or 1.8 kind of fell into that 50% ionic character. So, so they are connected and related and pretty much tell you the same thing. But and so we kind of do the majority rules, knowing that things is more of a continuum, but we do majority rules. And so large electronegativity differences, high percent ionic character, ionic bond, so above 50% or above that kind of 1.8, 1.7, 1.8 cutoff. And then small electronegativity differences, we get covalent bonding and sharing of electrons. And so we're going to do ionic bonding first, and then we'll look at covalent bonding and some of the properties. So as we talk about ionic bonding and we have that large difference in electronegativity, or again, high percent ionic character, and we kind of look at what happens there, we kind of see that when we have the formation of ionic bonds, if we look at sodium and chlorine, right, metals will lose their valence electrons, non-metals want to pick them up. And so when that happens, the sodium loses that one valence electron, chlorine takes it, finishes its octet. At that point, you have two ions formed, and those ions attract each other. And that's what that ionic bond is. So that ionic bond is really an electrostatic attraction. And because you have charged particles, those ions don't just attract one, they clump together. Now there is a pattern because they will clump together in a ratio so that the charge is balanced. Because you have a plus one and a minus one, you need one plus and one minus to balance out. So when those ions attract, they will form a crystal, and that crystal is going to have the number of ions in it in a ratio that is such that the charges will balance. So for sodium, where you have the sodium ion and the chloride ion with a minus one charge, okay, you need one plus and one minus to balance out. And so you would expect an equal number of sodium and chloride ions in a sample of sodium chloride. Okay. And so we get these nice solid crystalline structures when that happens, where if you count up the sodium chloride ions, you would see that you would have approximately equal numbers because you need a 1-to-1 ratio, right? And remember, and we'll talk more about formula writing, but remember the formula for sodium chloride is just NaCl because it gives the simplest ratio, not the actual number of ions. Right? Now, the fact that ionic compounds have this nice crystalline structure really does determine their properties. And so, if we look at, we'll come back to this picture in a few seconds, but if we look at some of the typical properties of ionic compounds, um, the simplest ones are metals and nonmetals, right? They do form lattices. So here's kind of a sample for sodium chloride. They do have relatively high melting point and high boiling points, and they can be soluble in water, but there are some ionic compounds that are not, but many are soluble in water. And they do have the ability to conduct electricity given the proper circumstances. Namely, when the ions are able to move, ionic compounds can conduct electricity. So there's two ways to get the ions moving. You can add heat and melt it so that the ions are able to move freely, or you can take the ionic compound like sodium chloride and dissolve it in water, and the dissolving process pulls those ions apart. And again, the ions are free to move, and then you have a solution that is able to conduct electricity. And so we call those type of substances electrolytes. Okay? So if you look back at our structure, we see that that crystalline structure gives ionic compounds some properties. Because it is crystalline and because there are these charged particles, they tend to be brittle. So if you add a stress, causes those ions to slide. If they slide enough and start sliding over an ion of the same charge, those ions will repel each other, and it will crack. So they tend to be brittle. They also tend to have a relatively high melting point because in order to melt them, you have to pull apart the ions from each other, which means you have to overcome that electrostatic attraction in between the ions, which means overcoming all those ionic bonds between them, so they can have a relatively high melting point and also boiling point. But as they are locked in this crystal structure, they won't be able to conduct electricity. Ions have to be moving. So we melt them, we're getting the ions to move because we're pulling the ions apart and allowing them to move around. We dissolve it in water. Again, we're able to get those ions to move around because now through the solvation process and through dissolving in water, we're able to, the water does the job of pulling the ions out of the solid and get them moving around. All right. So we have that bond really does determine the structure and a lot of the properties. If we kind of go back to our, again, flow chart, when we have a small difference in electronegativity, well, then that's when we have a covalent bond. We have, a small or no difference, and that covalent bond can form by a sharing of electrons. Now, this is kind of looking at the formation of a covalent bond between hydrogen atoms, each one having one valence electron. And so when they get close enough, right, the nucleus of a neighboring hydrogen atom will start attracting the valence electron of its neighbor. Now, because they are similar electronegativities, it's like having teams that have similar, on a tug of war, that are similar in strength. Either one can win and take that valence electron. And so you kind of have a stalemate where it has that nucleus has an attraction to its neighbor's electron, not enough to take it, so they end up having to share. And it's that sharing of those electrons that then fulfills in this case, gives each hydrogen atom 2 electrons in its valence shell. Again, for hydrogen, that's a really stable number. And sharing those 2 electrons makes a single covalent bond. And so we do have kind of those, that sharing of electrons. Now, that sharing of electrons is not always equal. Okay. And so as we talk and we kind of look at that sharing of electrons can be completely balanced and be a nonpolar covalent bond where the sharing of electrons is occurs evenly between the two atoms in the bond. This occurs between atoms that have very similar electronegativities, and so both atoms are of similar strength and attraction to electrons, and so they share evenly between them. When you have atoms that have larger differences in electronegativities, you run into a situation where one atom has a stronger attraction to electrons than the other, and you get uneven sharing where the electrons tend to hang around and be more attracted to that one atom. And so you get a polar covalent bond where there's a partial charge on either side of the bond, symbolized by these Greek letter delta, where the side with the more electronegative atom has a negative charge, or a partial negative charge because there's more electrons hanging around it, leaving the other side of the bond with a partial positive charge. And remember, ionic bonds are really polar bonds gone to an extreme, right? Where you have such a large difference in electronegativities that it's not just an uneven sharing, it's a complete transfer of electrons from one atom to another to make two independent ions with complete charges. Now, when you start having more than two atoms in a bond, right, you can have molecules that have a dipole moment. In other words, you can have the molecule as a whole be polar. And for that, you really have to take into account not only the polar bonds, but also their shape. And so we're not going to go into too much detail, but remember that you can have polar molecules where, because of the presence of a polar bond and the lack of symmetry, the molecule is polar. So there is, the molecule itself has a partial negative part and a partial positive part. And you can also have molecules that are non-polar, again, because of their shape and how the polar bonds are arranged. And so the shape can lead to symmetry, and molecules that are symmetrical are non-polar and have electrons shared evenly amongst them. Or they could be non-polar because there are no polar bonds. Right? And so, remember those polar and non-polar molecules can have some different properties because of that. If we kind of back out and take a look at our flow chart, and we look at kind of the properties of molecular compounds that results. So when we look at molecular compounds, remember molecular compounds are made up of discrete molecules. And so if you look at something simple molecular compound like water, right, its formula tells you exactly how many hydrogen and oxygen atoms are in each of those molecules. And so each one molecule of water has two hydrogens and one oxygen. Remember, it's different than like the formula unit you get for an ionic compound, which just gives the simplest ratios. And so sodium chloride as a solid has more than one sodium and one chloride ion. Okay? And the properties as well, because we have these discrete molecules, molecular compounds have some properties that are a bit different than ionic compounds. So unlike ionic compounds, right, the simple molecular compounds that we talk about are those binary molecular compounds between two nonmetals. And so they form molecules that have the covalent bond is very strong, holding the atoms together, but the attraction between neighboring molecules is much weaker than the intramolecular forces in the bond holding the atoms together. These simple binary molecular compounds tend to have low melting points and boiling points compared to the ionic compounds. Right? A lot of them are gases at room temperature. Water's unique in its properties that it's a liquid. They're not magnetic. Ignoring water, a lot of these binary molecular compounds are either sparingly soluble or soluble. It really depends on whether or not they are polar or nonpolar is if they're going to dissolve in water. So that statement is really a bit misleading. And so we're just going to cross it out. Because the molecules are not charged, they don't have, they're not ions, they're not moving, simple binary molecular compounds do not conduct electricity. And again, a good example is water. And so hopefully, this gave you a little bit of thought as to what we've been talking about. And we'll just kind of zoom out so we can kind of look through how these things fit together again. And again, we'll have a PDF of this. If you have questions, talk to your teacher, stop by office hours. Hope you all have a great week.